Okay, so the next talk is by Milad Barzegar on paving property of strong Rayleigh measures.
Okay, thank you. And thanks to the organizers. Nice to be here. This is a joint work with Rayleigh. Let me start by recalling a definition. Let X be a random subset of the set of integers from 1 to n, and mu be its distribution. So mu is a probability measure on the subsets of this set. Another way to look at this is that you can take X to be a random n-dimensional 0, 1 vector, and then mu becomes a probability measure on, say, a dimensional hypercube. I will mostly use the first point of view, but towards the end I will come back to the second point of view. So anyways, this X or mu is called strongly Rayleigh if this polynomial here is stable. I've used this notation, z to the power a is this monomial. And yeah, this polynomial is called the probability generating polynomial. Okay, so why is the definition important? This notion of strongly Rayleighness is the most natural notion of negative dependence. This was demonstrated by Borcha, Brandon, and Liggett. And here is a list of reasons for this statement. I'm not going to go through them. So let's continue. Now I will explain intuitively what I mean by paving property. So the setting is that we have this space of endpoints here, and we want to choose a random strongly Rayleigh subset of these points. As I mentioned, the points here are negatively dependent, and it means that there's this sort of repulsive force between the points. It means that if, for example, if you include a certain subset of these points in X, then the probability that any other subset, any disjoint subset is included in X drops. So yeah, there's this kind of repulsion between the points. Let me tell you what the paving property says. It says that it is possible to partition the space into a number of subsets such that the points in each of these subsets are almost independent. So these points are almost independent, these are almost independent, and so on. And the number of the subsets only depends on how much independence we want. Okay. So this is appealing from an intuitive point of view, because what it says is that this repulsive force between the points can't be strong everywhere. So for example, if the number of the points in the space are very large and we have fixed the notion of almost independence, then for example, in the largest subset of these sets in the partition, there's a lot of points that are almost independent, which are weakly correlated to each other. So I will show you a formal statement of this result, but before that I want to tell you a little bit about the ideas that we use in the proof and how we go about formalizing this idea. Okay, so I claim that this idea resembles the paving conjecture, which you are familiar with. So paving conjecture, which is a theorem now, it was proved by Marcus-Spielman-Srivastava, and I think in 2014, if I'm not wrong. So it states that for every positive epsilon, there is an integer r, which only depends on epsilon, such that every Hermitian matrix M with 0 diagonal can be R epsilon paved. And this means that if M is n by n, so number the rows and the columns by 1 to n, then the set can be partitioned into R subsets such that this holds here. Here, this is the operator norm, and this is the principal submatrix of M, which is the intersection of the rows and columns with numbers in SK. Okay, so how does this connect to the paving property? This happens in the case of determinantal point processes. So let X be a random subset of the set. This is just a finite point process. Discrete point process. So this X is called determinantal if there is a Hermitian matrix K such that this happens. For every A, the probability that A is included in X is just the determinant of the corresponding principal submatrix. And K here is called the kernel of this determinantal process. It is known that these point processes are in fact strongly Rayleigh, and the nice thing about them is that everything can be expressed in terms of a matrix, so it makes things much easier. So let me recall some facts about determinantal point processes. The first one is that a Hermitian matrix is the kernel of a determinantal process if and only if all of its eigenvalues are between 0 and 1. I will not use it right now. I will use these two facts in the next slide, which follow easily from the definition. The first one says that X is independent if and only if its kernel is diagonal, and independent means that it chooses the point, this random subset chooses the points independently. And the second one says that the restriction of X to any subset like A is itself determinantal, and its kernel is just the corresponding principal submatrix. Okay, and I mentioned that these are strongly Rayleigh, and also their probability generating polynomial has this form here. Here Z is just the diagonal matrix of the variables. So, okay, let's now deduce the paving property for determinantal processes. We need a Hermitian matrix with 0 diagonal, so we subtract the diagonal and we can apply the paving theorem to this matrix. Then for any epsilon, we get a partition like this here, such that this holds. On the right-hand side here, we should have a operator norm of K0, but it's easy to see that it is less than 1. And what this says is that on the left-hand side, what we have is this principal submatrix, which is just the kernel of this restriction of X to SK. And we have this matrix, which is diagonal. It is in fact the diagonal of this matrix here. So what this says is that for each SK in this partition, the kernel of this restriction of X to each of these subsets is almost diagonal. So, and I mentioned diagonal independence. So this, in a sense, means that the points in each of these sets are almost independent. Okay. Now, there are two problems. The first one is that the statement in the previous slide wasn't a nice one from a probabilistic point of view. So we would like a probabilistic statement. This doesn't look like a hard problem. This looks easy to deal with. But the second problem is how to deal with the strongly Rayleigh case, and this looks a little bit more scary. And I want to talk about how we deal with these problems. First, I will answer the second problem, because the nature of the first problem will change once I do that. So how do we answer the second problem? We extend the paving theorem to real stable polynomials. This might look like a crazy idea at first, but it actually is a natural thing to do. And the reason is that in Marcus and company's paper, they use the two main steps are which are called interlacing families and the barrier method. Both of them concern real stable polynomials. So this is hopeful in a way. But what they do is that they use these methods to prove Weaver's conjecture, which is actually equivalent to the Paving conjecture. And it has this vector balancing formulation. And they also deduce the Paving conjecture from this Weaver's conjecture. So anyways, the problem is that the proof really goes in a direction that's doesn't really generalize to polynomials. So yeah, the ideas in this proof do not directly actually extend to real stable polynomials. So let me show you their paving result. They prove that for any Hermitian matrix with zero diagonal, there is this partition such that this happens. So they obtain this paving bound here. There is this relation between the paving bound and the number of the sets in the partition. Okay, but there is this paper by Leek and Ravichandran, and they come up with a direct proof of the paving conjecture. The upshot is that they get a better paving bound, but for us, the nice thing is that the proof actually generalizes to polynomials. It actually gives you an idea about how to formalize an extension of this results to real stable polynomials. And also, again, their main methods are interlacing families and a new version of the barrier method. So those work for real stable polynomials. But of course, there are steps that they use facts from linear algebra. They prove things about this Hermitian matrix. But we were able to just, all the steps actually come through, but we needed to come up with new proofs for some of the steps. And we did that mainly using interlacing properties of real stable polynomials together with some simple facts from majorization. So let me show you our results. I'm going to use these notations. The first one I think is standard. This is for a multivariate polynomial. Its diagonalization, which we denote by p bar, is this univariate polynomial here. And the last one says that if q is a real-rooted polynomial and lambda I are its roots, then m of q is just the maximum absolute value of its roots. This is gonna play the role of operator norm. So if you put the characteristic polynomial of a Hermitian matrix here, you just get the operator norm. So yeah, this is our result. The constants are the same as Leek and Ravichandran's result, but we have replaced polynomial matrices with polynomials. So we prove that for every multi-affine real stable polynomial, such that the leading coefficient is equal to 1. This one is not special, it just needs to be non-zero, I think, or maybe positive. But I'm gonna just use this case here. I'm just gonna use this case, that's the leading coefficient is 1. And these coefficients are 0. These are the coefficients of the monomials of degree 1 less. This replaces the assumption that the diagonal of a matrix is 0. Then we have this partition such that this happens here. So it is a well-known fact that if P is real stable, then its diagonalization is real-rooted. So this is well defined here. On the left-hand side, we have this weird thing we differentiate with respect to the variables outside of SK. It is known that this preserves real stability. So the diagonalization is real-rooted, and again, this is well defined. Okay, let me show you how Leek and Ravichandran's results follow from this. If you apply our theorem to this polynomial here, this is called the multivariate characteristic polynomial of A. Z is again the diagonal matrix of the variables. And yeah, it is well known that this is real stable. It's easy to see that it is multi-affine. its leading coefficient is 1, and if its diagonal is 0, then these coefficients become 0. And also, if you differentiate with respect to outside of Sk, you just get the multivariate characteristic polynomial of the principal submatrix corresponding to Sk. Okay, so this is our polynomial paving results. Now let's go back to strongly Rayleigh measures. So we need to apply our theorem to a real stable polynomial. The first candidate is the probability generating polynomial, but this isn't good because these derivatives don't have a really good interpretation. So let's do the obvious thing and compare with determinantal measures. For determinantal measures, we have these two polynomials. This is the probability generating polynomial, and this is the multivariate characteristic polynomial of the kernel. And to obtain the paving property, we need to apply our theorem to this polynomial. But in the strongly Rayleigh case, we only have the probability generating polynomial. So the question is, what is the polynomial that corresponds to this polynomial? So again, we can do something simple. We find a transformation that takes this polynomial to this polynomial, and we just apply it to this polynomial. So let's do that. This is the transformation, and we get this polynomial. We can compute its coefficients. One thing is that the coefficients are nice. These probabilities appear as the coefficients. And also this object, which we call the kernel polynomial, appears to be a nice object. In some problems, in some settings, it's more natural to actually look at this polynomial rather than the probability generating polynomial. For example, in our problem, this is the case. So let me show you some of the properties of this kernel polynomial. One thing is that this kernel polynomial is actually plays a very similar role to the kernel of the determinantal processes. So yeah, the first fact is that this polynomial is real stable. The second one is that a multi-affine real stable polynomial with leading coefficient 1 is a kernel of a strongly Rayleigh measure if and only if the roots of its diagonalization are between 0 and 1. So this is similar to the fact that a matrix is kernel of a determinantal process if and only if its eigenvalues are between 0 and 1. And in fact, these roots play a very similar role to the eigenvalues of the kernel of a determinantal measure. So one fact about determinantal measures is that those eigenvalues play an important role. The same thing happens here. Yeah, I don't have time to go through this, but I will show you an example of this important role later. And the fact that I will use right now is that if you restrict to any subset, then this restriction is again strongly Rayleigh. And the nice thing is that its kernel is just this take derivatives with respect to the variables outside of A. Okay, so now we want to apply the paving theorem. But we needed some coefficient, the coefficients of the monomials of degree 1 less to be 0. So we define this polynomial here. Here, pi are just these probabilities. And as I mentioned before, these are the coefficients of these monomials. So this polynomial has these properties. It is multi-affine real stable. The leading coefficient is 1. These coefficients are 0, so we can apply the paving theorem to this polynomial here. And also m of f bar is less than or equal to 1. Okay, so now let's apply the paving theorem to f. Then we get a partition such that this here happens. Again, on the right-hand side, we should have a m of f bar, but it was less than 1. And this is, let me show you again, this is a similar polynomial to this for the restriction of x to sk. Okay. So what we want to do now is to interpret this to these restrictions to being almost independent, which takes us back to the first problem, which has become a little bit harder right now. So how do we solve this problem? We do that by finding a connection between the entropy of x and the roots of the kernel polynomial. Okay, so yeah, in particular, we use the notion of entropy to formalize the idea of almost independence. Okay, let me just recall that this is the definition of entropy. I will not use it, but let's look at this fact. If x is a random vector, then we have this inequality here. Its entropy is less than this. And a simple observation is that this is just the entropy of the independent version of x, which means that this x hat is just a random vector whose components are distributed as the components of x, but they are independent. So the entropy of x is almost always less than the entropy of its independent version. So for a certain x, we can prove that these two sides are close to each other. It is a nice formalization of the idea of almost independence. Okay, so first let me show you the connection between the entropy of x and the entropy of the roots of the kernel polynomial. So if lambda I are the roots of the kernel polynomial, then we have this inequality here. Recall that lambda I were just between 0 and 1, so this right-hand side is well defined. Okay, this theorem is actually nice on itself, but yeah, we use this, and this is the main step in the proof of the paving property. So yeah, let me finally show you this result. This says that for every positive delta, there is an integer which only depends on delta, such that for every strongly Rayleigh point process x, it is possible to partition the underlying space into R subsets such that this happens. Okay, this is the left-hand side. This is just the entropy of the restriction of x to sk, and this is the entropy of its independent version. So this says that the difference between these two entropies is less than this. Unfortunately, there's the size of sk here. I don't think that we can eliminate this, but if this didn't appear here, this would be a very strong result, but yeah, this appears. One way to make it nicer is to just divide both sides by size of sk. So if you do that, you get the mean entropy per particle of these two processes. So yeah, this is the mean entropy per particle. This shouldn't be here. This is less than delta. So this implies that the mean entropy per particle of this restriction is close to its independent version. So yeah, this is our formalization of the idea that I told you about. Okay. So I think I have a couple of minutes to go through these open questions. The first one is applications, both for the polynomial paving theorem and the paving property for strongly Rayleigh measures. I had this idea that it might be the strongly Rayleigh paving property could be useful to prove that some measures are not strongly Rayleigh. So yeah, for example, one example that I tried to apply this was the Gaussian threshold measure, which is known to be negatively associated. but we don't know if it is strongly Rayleigh or not. But I wasn't really successful in doing that. So it would be nice to find applications for these theorems. And the next two problems are connected to the entropy lower bound. The first one, so let me go back to the entropy lower bound. So one way to look at this is that if these are independent Bernoulli variables with parameters lambda1 to lambda n, then this right-hand side is just the entropy of this random vector. So this just says, this becomes just this inequality here. And the second question asks if the distribution of this random vector majorizes the distribution of x. So if it happens, then because H is short concave, then this follows. So it is actually stronger than the paving, than the entropy lower bound. And the nice thing is that it is true for determinantal measures. And the way we can prove this is using this result that expresses a determinantal measures as a mixture of projective determinantal measures, which means projective determinantal measures are determinantal measures with fixed size. So the last question is even stronger than the first one in a sense. It asks for a similar result for strongly Rayleigh measures. It asks if it is possible to express a strongly Rayleigh measure as a mixture of strongly Rayleigh measures with fixed size. Okay, so if we can do this, and if we characterize this mixture nicely, then the second problem follows. And I don't know, I think, I don't know if this is possible. It is possible to prove such a result because the same result for determinantal processes uses spectral theorems. So we don't have a similar thing here. But the eigenvectors of the kernel matrix play an important role in this mixture for determinantal measures. So we don't have a similar object for polynomials. So I'm not really hopeful that this would hold, but yeah, I don't know. So yeah, I will stop here and thank you for listening.
Thanks a lot, Milad. It was a really nice talk. Any questions? Could you say a bit more about what you mean by a nice mixture? So you can write it as some mixture, but so what exactly does nice mean?
It would be nice means that you can express those strongly Rayleigh measures with fixed size. You know, you should have a nice expression for these. For example, in the determinantal case, those projective measures have a relationship with the how should I say this? Let me say it this way. Nice means that you should be able to express these strongly Rayleigh measures with fixed size in a nice way in terms of the original strongly Rayleigh measure, right? Mm-hmm. For example, in the determinantal case, you can do that in terms of the eigenvectors of the kernel of the original determinantal measure. But in here, I don't know how does that work.
But if you condition on the number of points in the subset, that conditioned measure is still strongly Rayleigh. So the issue is the mixture, right?
Right.
Mm-hmm.
Right. Yeah. What I want actually is a direct generalization of the similar result for determinantal measures. That would be really nice.
So do you, so one question is, you do not expect, or I do not expect this to be algorithmic yet, right? You have, even for some, your main theorem, even for like spanning trees, have you thought about it? Is it possible to make it algorithmic?
Yeah, no, we haven't really thought about it. I don't know. I have no idea. You mean the strongly Rayleigh paving, right?
Yeah, in the last slide.
Excuse me, can you repeat the question?
Oh,
can you repeat the question? Thanks.
I guess so if you go back to the last slide, it basically says that you can partition the edges of a spanning tree, of a graph, into these constant number of sets, such that essentially every set is independent.
Yes,
so
that
I was
got,
wondering, I was wondering if you can make this algorithmic. Like
okay. Thanks a lot. Thanks.
Sure.
Yeah,
but
it is a good idea, a good question, but I have no idea. Yeah, I haven't really thought.
But it seems to me, at least, this SK is necessary in that case. Like, for example, if you have a complete graph, I don't think you can get rid of the SK.
Oh.
I mean, I'm not sure, but it seems.
Yeah, I think that it is impossible to do this. I mean, if you look at the proof, it really.
I say you can construct counterexamples. That there is no way to.
Yeah, I don't know.
I mean, there has to be some scaling in the size, right? Because you could make the thing bigger and bigger, and then delta would basically be 0. I mean,
right.
I'm guessing
the point is,
mm-hmm.
The point is you want to see if you can make delta independent of the size or not, right? If you drop, but if delta is independent of the size, then this is huge, right?
It sounds very fishy.
Exactly.
But
Right.
And this property, I mean, do you expect it to generalize to some measures that possibly are not negatively dependent, but have some controlled behavior, like the log concave ones, or is there some simple counterexample?
Oh, yeah. Good question again. I haven't really thought about it. I don't know. But I don't think that our proof would work for that. We really use strongly real stability. We use a lot of interlacing properties, so.
It's interesting. It's interesting because this sort of, I mean, this lemma that you have, that you relate the entropy to the roots, the entropy of the roots, that one doesn't seem to. I mean, I don't know how to generalize that to log concave distributions.
Right.
And you said you use the entropy in the existence proof as well, or no? The entropy is only used in the part 1.
Existence.
Sorry, there are 2 parts, right? There's the.
Yeah. Existence only follows from the paving, polynomial paving result. We only use it here.
Which doesn't use this notion in any way.
Right.
Okay.